There is something deeply wrong with how we cool our buildings today. In 2019, researchers from MIT ran temperature tests on buildings in Timbuktu, Mali. Outside, the Saharan sun pushed the mercury to 118 degrees Fahrenheit. The sand was hot enough to blister bare feet in seconds. Modern concrete buildings with metal roofs, the kind we export across Africa as development, hit internal temperatures of 95 degrees Fahrenheit, even with windows open. Occupants sat sweating, miserable, waiting for sunset. Just 3 blocks away stood a traditional mud brick home built in 1640. Same scorching sun, same brutal heat. Inside temperature, 72 degrees Fahrenheit. No air conditioning, no electric fans, no solar panels or evaporative coolers. The structure itself, built from dirt and straw using methods we call primitive, kept the interior 46 degrees cooler than the air outside. Cut the power to a modern American home when it's 105 degrees Fahrenheit in Phoenix. Within 3 hours, the indoor temperature hit 90 degrees Fahrenheit. By 6 hours, it's uninhabitable. People die. It happens every summer during blackouts. Elderly residents are found dead in their own living rooms, killed by buildings that can't function without constant energy input. What did African builders know 400 years ago that we have completely forgotten? Across the Sahel, from Senegal to Sudan, thousands of earthen structures built between the 11th and 18th centuries are still standing. These buildings have endured summers that would turn a modern stick-built house into an oven within hours. They achieve this with 3 principles that are completely absent from international building codes: thermal mass, evaporative cooling, and strategic airflow. These weren't separate tricks. They formed a complete system that worked with the sun, not against it. Today we fight heat with brute force electricity. We pump refrigerant through compressors, blast cold air through ducts, and wonder why our energy bills are bankrupting us. Before we go deeper, drop a comment below. Have you ever experienced a power outage during a heat wave? How long before your house became unbearable? An hour? 3 hours? Or was it already cooking after 30 minutes? Let us know, because what you're about to learn will change how you look at every modern building. Let's rewind to 2015. A team from the École Polytechnique Fédérale in Switzerland ran a controlled experiment in Burkina Faso. They constructed 2 identical-sized dwellings, both roughly 500 square feet. The first was a reconstructed traditional Gurunsi compound house. Mud walls 16 inches thick, handmade from laterite clay mixed with rice husks, thatched roof of woven guinea grass, elevated with an air gap. No modern materials, no cement, no steel. The second was a contemporary concrete block house built to current West African urban standards. Cement blocks 8 inches thick, corrugated metal roof, glass windows, painted interior. On paper, the modern house looked superior. Both structures sat in the same compound. Outside temperature, 118 degrees Fahrenheit, 2 p.m. Both started the morning at 75 degrees Fahrenheit. Then they sealed the doors and let the sun do its work. The concrete house climbed 98 degrees Fahrenheit within 4 hours. By sunset, it was 105 degrees Fahrenheit inside. Even after dark, the walls radiated stored heat. Midnight, it was still 91 degrees Fahrenheit. Sleeping inside required a fan at minimum. The mud house? After 8 hours of full sun, the interior temperature peaked at 90 degrees Fahrenheit. By sunset, it had dropped 76 degrees Fahrenheit. By midnight, it was 72 degrees Fahrenheit, actually cooler than it started. Occupants slept comfortably under a thin cotton sheet. A modern engineer might say this violates thermodynamics. The concrete house has better compressive strength. The metal roof reflects more solar radiation than thatch. The glass windows have a higher R value than wooden shutters, so the modern house should win. But this completely ignores thermal mass, and thermal mass changes everything. A 16-inch laterite mud wall weighs about 140 pounds per linear foot. Clay has exceptional specific heat capacity, meaning it can absorb massive amounts of thermal energy before its temperature rises. When the sun beats down, the outer surface heats up, but that heat takes 8 to 12 hours to penetrate through 16 inches of dense earth. By the time the heat reaches the interior wall surface, the sun has set and the outside air is cooling. The wall never transfers its peak heat load into the living space. The concrete house operates on a completely different thermal cycle. Concrete blocks are only 8 inches thick and much less dense than compressed clay. They heat through in 3 to 4 hours. Worse, the metal roof is a thermal disaster. Corrugated steel under direct Saharan sun reaches surface temperatures of 160 to 180 degrees Fahrenheit. That radiates directly into the ceiling cavity. There's no thermal mass above to buffer it. The heat just pours straight down into the living space. The result is a building that cooks its occupants. Ancient African builders understood thermal lag instinctively. They used laterite clay, a material formed from weathered tropical rock rich in iron and aluminum oxides. This clay is incredibly dense when properly compressed. 1 cubic foot weighs over 100 pounds. Compare that to concrete at 145 pounds per cubic foot, but concrete is used in thin shells. A typical concrete block wall has hollow cores. The actual mass per square foot is much lower. A solid mud wall has no voids, no air gaps. It's pure thermal battery. But mass alone isn't the full story. Clay does something concrete can't. It breathes. Earthen walls are microporous. They allow water vapor to pass through while blocking air infiltration. In the dry heat of the Sahel, this creates passive evaporative cooling. During the night, the walls absorb moisture from the cooler air. During the day, as the outer surface heats, that moisture evaporates. Evaporation is an endothermic process. It pulls heat away from the wall surface. This is the same physics that makes sweating cool your body. The wall is essentially sweating. A 2017 study by the University of Khartoum measured this effect. Traditional Nubian mud walls lost up to 8 degrees of surface temperature compared to sealed concrete walls purely through evaporative cooling. That might not sound like much, but over a 16-inch thick wall with massive thermal inertia, it compounds. The heat never builds up. It's bled off continuously through evaporation and radiation to the night sky. Concrete and cement block walls can't do this. They're sealed. Moisture can't escape, so there's no evaporative benefit. The heat just accumulates. And once concrete is hot, it stays hot for hours because it has thermal mass but no cooling mechanism. The roof was the second critical component, and this is where African design reaches genius level. We think of thatched roofs as primitive, something you upgrade away from as soon as you can afford metal. But thermally, thatch is vastly superior to any modern roofing material. A traditional Sahelian thatched roof is not just straw thrown over beams. It's a sophisticated 12 to 18-inch thick woven structure made from guinea grass, elephant grass, or palm fronds, depending on the region. The thatch is bundled tight and layered in overlapping courses. This creates two things: massive thermal resistance and an elevated air cavity. The R value of thatch is around 3 per inch. A 15-inch thick roof has an effective R value of 45. That's better than most modern insulated roofs. But the real magic is the air gap. Thatched roofs were built on a frame that held the thatch 12 to 18 inches above the mud ceiling. This gap allowed air to flow continuously. Hot air rising from the sun-baked thatch escaped out the ridge vent, pulling cooler air in from the shaded eaves. The thatch itself never transfers heat to the living space because there's a convective barrier in between. Compare this to a metal roof bolted directly onto ceiling joists. The metal is a direct conductor. Heat transfers immediately from the roof into the attic space, then radiates down through a thin plywood or gypsum ceiling. You end up with a ceiling surface that's 95 degrees Fahrenheit or hotter that radiates straight onto your head. Thatch also has one more advantage. It reflects and scatters solar radiation. The rough fibrous surface doesn't create the mirror-like reflection of metal. It diffuses the light, and because it's organic, it stays cooler to the touch. A metal roof in full sun is untouchable. A thatched roof you can place your hand on. A 2012 study in northern Ghana compared identical buildings with thatched roofs versus metal roofs. The thatched buildings averaged 14 degrees and cooler during peak afternoon heat. That difference is life or death in a heat wave. The third element is strategic airflow, and this is where traditional African architecture becomes truly elegant. Sahelian builders didn't just make thick walls and good roofs. They designed entire structures to channel wind. The Hausa people of northern Nigeria perfected this. Their traditional compounds feature a central courtyard surrounded by rooms. The courtyard acts as a thermal chimney. During the day, the sun heats the courtyard floor. Hot air rises and escapes over the walls, creating negative pressure. This pulls cooler air from the shaded rooms through carefully positioned doorways and small, high windows. The airflow is continuous and self-regulating. No fans, no electricity, just physics. In hotter regions, they built wind towers called malkaf in Arabic, or ventilation towers in English. These are vertical shafts rising above the roofline with openings facing the prevailing wind. Wind hits the tower and is forced down into the building. The cool air, which is denser, sinks to the floor and spreads through the rooms. Hot air exits through roof vents on the opposite side. The Tuareg nomads used a portable version of this. Their traditional tents had high-peaked roofs with adjustable flaps. The flaps opened to catch the wind, channeling it down into the living space while allowing hot air to escape through the peak. Even in 115 degrees Celsius heat, the interior of a well-positioned Tuareg tent could be 20 degrees Celsius cooler than outside. Modern buildings ignore airflow entirely. We seal everything tight for HVAC efficiency, then rely on mechanical systems to move air. When the power fails, the building becomes a stagnant oven. There's no passive ventilation. Windows don't align to catch cross breezes. Rooms are deep and blocked. Air can't flow. A 2020 study by the Kwame Nkrumah University in Ghana found that modern urban apartment blocks in Accra routinely hit 97 degrees indoors during power outages, while traditional courtyard homes in the same neighborhood stayed at 90 degrees Fahrenheit. The difference was airflow design. The traditional homes were built to breathe. The modern ones were built to depend on air conditioning. Interior design was just as intentional. Traditional African homes didn't use open floor plans. Modern open concept designs are a thermal nightmare in hot climates. Heat spreads everywhere. There's no way to isolate cool zones. Traditional compounds divided space into small, purpose-specific rooms separated by thick walls and doorways with heavy curtains or wooden doors. This created thermal zoning. The outer rooms, exposed to sun, were used for storage or daytime work that could tolerate heat. The inner rooms, shaded by the outer structure, stayed cool and were used for sleeping and refuge during peak heat. Cooking was done outside or in a separate structure entirely, so the heat and smoke didn't warm the living quarters. The Dogon people of Mali took this further. Their cliff dwellings were carved into rock faces with living spaces recessed deep into the stone. The rock itself, several feet thick, provided massive thermal mass. The overhanging cliff shaded the openings. Inside, the temperature stayed near constant year-round, hovering around 68 to 72 degrees Fahrenheit, even when outside temps swung from 50 degrees at night to 118 degrees Fahrenheit during the day. This is passive geothermal conditioning. The Earth's temperature below the surface is stable. By building into it, you tap into that stability. Modern homes try to heat and cool every room to the same temperature, 24/7. It's thermally insane. You're pumping energy into spaces nobody is using. Traditional design was ruthlessly efficient. You only conditioned the space you occupied, and you did it passively. Bedrooms were cooler because you slept during the coolest part of the day, the early morning. You didn't need to cool them artificially. Living spaces stayed comfortable through thermal mass and airflow. There was no wasted energy because there was no energy input to waste. A 2018 analysis of traditional Moroccan riads found that the thermal zoning strategy reduced the need for active cooling by 60% compared to a modern equivalent-sized building. And this is in urban Morocco, where traditional design has already been compromised by modern influences. So why did we stop building this way? The answer is the same as always: colonialism, speed, and cheap energy. When European powers colonized Africa, they brought their own building materials and methods: concrete, steel, glass. These were symbols of modernity and progress. Mud was seen as backward, primitive, a sign of poverty. Indigenous building techniques were actively suppressed. Colonial administrators built government offices, schools, and hospitals using European designs that were completely unsuited to the climate. Concrete boxes with metal roofs, buildings that required constant ventilation or early air conditioning to be habitable. This set the standard. Newly independent African nations inherited these buildings and the assumption that this was the correct way to build. Mud and thatch were things to escape, not preserve. Then came the oil boom. In the 1960s and 70s, energy was incredibly cheap. Air conditioning became affordable. Why bother with thick walls and clever Ventilation when you could just install a window unit? Developers started throwing up cheap concrete block housing as fast as possible. Speed was everything. A concrete block house could be built in weeks. A traditional mud house took months. Labor costs were rising. Concrete was mass-produced and standardized. And there was another factor: durability myths. People believed concrete lasted longer than mud. This is false. Properly maintained earthen structures last centuries. The Great Mosque of Jenne in Mali has stood since the 13th century. It's replastered annually, but the core structure is original. Concrete, meanwhile, begins to degrade immediately. Rebar rusts. Moisture infiltrates. In tropical climates, concrete buildings start crumbling within 30 years, but the myth persisted, fueled by marketing from cement companies. The result was a construction boom across Africa using the worst possible materials for the climate: cheap concrete blocks, uninsulated metal roofs, poor ventilation, buildings designed to require mechanical cooling in regions where electricity is unreliable and expensive. We created an entire continent of homes that are uninhabitable without air conditioning in places where most people can't afford to run it. But the knowledge isn't dead. Across Africa, architects and engineers are rediscovering traditional techniques and validating them with modern science. In Burkina Faso, architect Diabedo Francis Kéré has built award-winning schools and hospitals using compressed earth blocks and natural ventilation. His designs combine ancient thermal mass principles with modern structural engineering. The buildings stay cool without air conditioning, even during 112 degrees Fahrenheit heat waves. They've won international architecture prizes not for nostalgia, but for performance. In Egypt, the Hassan Fathi Institute is reviving Nubian vault construction, a method of building domed roofs from mud brick without any scaffolding or formwork. These vaults create superior airflow and thermal performance compared to flat concrete roofs. Homes built with this technique use 70% less energy for cooling than conventional builds. Science is backing this up. A 2021 study by the University of Bath tested compressed earth block buildings versus concrete block buildings in Kenya. The earthen buildings maintained internal temperatures 12 to 18 degrees Fahrenheit cooler during the day with zero energy input. Residents reported better sleep, less heat stress, and massively lower electricity bills. The earthen walls also regulated humidity naturally, preventing the mold issues that plague concrete buildings in humid regions. Then there's the carbon issue. Producing 1 ton of cement releases nearly 1 ton of CO2. Concrete is responsible for 8% of global carbon emissions. Earthen construction has near zero embodied carbon. The clay is dug locally, mixed with water and straw, and compressed. No firing, no chemical reactions, no emissions. A traditional mud brick house has a carbon footprint 95% lower than an equivalent concrete house. As the world wakes up to the climate crisis, this matters. We can't keep building with materials that destroy the planet and then require fossil fuel energy to keep the buildings habitable. There's a massive movement now in architecture schools across Europe and North America studying African vernacular design, not as anthropology but as engineering. These techniques work. They're not romantic relics, they're superior solutions that we abandoned for bad reasons. If you're building or renovating a home in a hot climate, you can steal these principles right now. You don't have to live in a mud hut, but you can use thermal mass. Look into rammed earth, compressed earth blocks, or even modern autoclaved aerated concrete, which has better thermal properties than standard concrete. If earthen walls aren't an option, integrate thermal mass inside the building. Thick interior adobe or brick walls, stone floors. These act as thermal batteries that stabilize temperature swings. Focus on the roof. If you're in a hot climate, never use an uninsulated metal roof. If metal is unavoidable, create an air gap. Build a false ceiling with ventilation to allow hot air to escape. Better yet, use thatch, tile, or thick wooden shingles. These materials have thermal resistance and don't turn into radiators under the sun. Design for airflow. Map the prevailing winds and position windows to create cross-ventilation. Use high vents or cupolas to let hot air escape. If you're in an urban area with no breeze, consider a solar chimney, a modern version of the African wind tower. It uses sun-heated air to create updraft and pull cool air through the building. Use thermal zoning. Stop trying to cool your entire house to 70 degree form. Cool the spaces you occupy. Let storage rooms, garages, and unused bedrooms run warmer. Close doors. Use thick curtains. Think like a traditional builder. Control the heat. Don't fight it everywhere at once. And think long term. A house that costs more upfront but slashes your energy bills and stays comfortable during blackouts is the smarter investment. Modern codes obsess over initial cost and compliance. They ignore resilience, comfort, and life cycle value. The Sahelian farmer in his 400-year-old mud home wasn't primitive. He was a master of thermodynamics. He knew heat moves slowly through mass. He knew evaporation cools. He knew wind is free energy if you design for it. We traded that knowledge for air conditioning and concrete. Now, as energy costs skyrocket and grids fail, we're paying the price. If you found this valuable, hit that like button and subscribe. We're digging up the ancient knowledge that modern construction would rather you forget. These African techniques weren't accidents. They were refined over thousands of years. The buildings that failed the summer heat killed their occupants. The ones that worked were copied and passed down. What survived was a system so robust it kept families alive in 180 degrees Fahrenheit. Heat with zero electricity. They weren't just surviving. They were comfortable, healthy, building civilizations. The secret wasn't lost. It was buried under colonialism and corporate marketing. Every time you choose thermal mass over air conditioning, natural ventilation over HVAC, and thoughtful design over brute force energy, you're bringing that wisdom back. Wisdom that kept people cool when the world was brutal. Wisdom that still works.